Thank you everyone so much for joining us this afternoon for our webinar on how to accelerate life science and diagnostic imaging instrument development. During today's webinar, we're going to cover the architecture considerations when building a fluorescent microscope, the challenges of microscopy instrument development and COTS microscope limitations, as well as how to optimize automated motion and imaging design in your instrument. Just a few housekeeping items before we jump in. We are recording the webinar and we'll send out the link to the recording after the event to all of the attendees. Also, we did allow for some time for questions at the end. So as we review the material, please feel free to post your questions in the chat and we'll address them at the conclusion of the presentation. We've got three amazing presenters with us today, Jim Feeks and Joe Mully from IDEX and Kevin McCarthy from Dover Motion. And with that, I'll turn it over to Jim to introduce himself.
Hey, good afternoon, everyone. My name is Jim Feeks. I'm a lead optical systems engineer with IDEX Health and Science. I've been with the company for almost 7 years now. And during that time, I've focused mostly on the design, build, and test of our full source-to-sensor systems. Prior to that, I did my PhD at the University of Rochester in the Institute of Optics.
Hello, I am Joe Mully. I'm a principal optical engineer. I've been with IDEX Health and Science for about 13 years, but my overall focus and experience has been in lens design for 19 years. I started out working with and developing zooming microscopes, later expanding into semiconductor inspection and broader microscopy applications. And in recent years, I've been working almost exclusively on fluorescence microscopy systems, including high-performance water immersion microscopy. Kevin?
Hi, I'm Kevin McCarthy, Chief Technology Officer for Dover Motion. I have been with the company for 43 years now, and I have to say I'm still having a blast and really am privileged to be able to work with our very talented customers and partners as they develop really cutting-edge life science and diagnostic instruments. We do our best to support that via our motion capabilities.
All right, so before we start, I just wanted to give a brief overview of IDEX Health and Science. So IDEX Health and Science is part of IDEX Corporation. And within that umbrella, we have our Life Science Optics group, which is the group that Joe and I are a part of. So within the Life Science Optics group, we have 2 sites. The first is in Rochester, New York, where we focus mostly on our design and build of imaging optics and filters, as well as the optomechanics that allow all of those components to go into a microscope. Our Carlsbad, California site focuses more on the illumination and autofocus side of things with the design and prototyping of those submodules. And then all of that work is then transferred to the Rochester site for manufacturing. So as you can see here, we have a breadth of experience in all of the submodules that go into a fluorescence microscope. So from illumination, high power lasers, providing flat top illumination and laser autofocus systems, to high NA large field of view imaging optics and the filters that allow you to get light where it needs to go, as well as all the optomechanics that allow you to get those things aligned into a highly performing microscope. So if you're looking to design a new microscope and want to partner with us on any of the components, submodules, or even the full system, let us know. Kevin?
Here at Dover Motion, in a nutshell, what we do is we move things back and forth, up and down, mostly back and forth. And this is central, as we'll see, to automated life science and diagnostic imaging instruments. We do so with a very high degree of precision, but our major value proposition is on throughput. So we're really aiming to get the maximum number of images possible out of your sample. And that's certainly an important part of the cutting-edge instrument. Recently, we've developed what we call our smart stage ecosystem, in which what would traditionally have been bulky bit of external control electronics has actually been highly miniaturized and dropped directly into each axis. And that's really shrinks the size of the instrument. And yet we've actually managed to take performance up rather substantially.
All right, so getting into the content. So I thought during my section of the webinar, I would talk about what I'm calling fluorescence microscope architecture considerations. But what that really means is taking a holistic design approach to your microscope, thinking about how all of your components and subassemblies are going to work together so that you have a fully optimized system that will then provide the highest performance possible. So I'll go into a few of those topics, but first I just wanted to cover an overview of some of the major components in a fluorescent microscope. So starting from where the light begins, right, we have our autofocus and illumination modules on the left side of the image there. That autofocus is there to ensure that your objective can be focused and ensure that your sample is then in focus. Illumination, of course, provides excitation to excite the fluorescence from your sample. You then have a couple of dichroics. The first combines that autofocus and illumination and directs that light towards the objective. You then have an excitation injection dichroic, which reflects that excitation and autofocus light while allowing the fluorescent emission to pass through. That light then encounters the objective, which is sitting on a focusing stage, allowing it to move up and down in order to ensure your sample is in focus. That light then goes down and moves into the sample where it excites that fluorescence. The samples are typically much larger than the imaging field of view of your objective, so those samples will sit on an XY stage, allowing you to move back and forth to image the entire sample and collect all your data. After that, fluorescence is excited and subsequently emitted. It then transfers through that excitation injection dichroic through an emission filter, which will clean up any residual excitation as well as unwanted fluorescence or even stray light, and then focused onto a camera with your tube lens. So those are the main components there, and you can see that all those components in gray are things that are manufactured by IDEX Health and Science, and the components in blue are manufactured by Dover Motion. But what I wanted to stress here is that all of those components need to really work together in order to ensure that you have the most highly performing microscope you can, right? You don't want your illumination module to be illuminating one size field of view while you're actually trying to image something much larger or much smaller, as an example. And there are many of those types of examples when thinking about system design. So just briefly, I wanted to show what that might look like. Previously, it was just a block diagram, but this is what a microscope like that might look like in CAD form. So again, you can see your imaging optics, your autofocus and illuminator, filter block that has that excitation dichroic, and then of course your sample, which is sitting on an XY stage. In this case, we're showing it with vibration isolation as well. So you emit that fluorescence, it goes up through the objective, reflects off of a fold mirror in order to keep the system size down, and then is focused onto the camera with the tube lens. So I wanted to cover 5 main topics today. The first is just very basic. Where do you start when designing a fluorescent microscope? The second and third are both involving cameras. The first is, how do you select the right camera for your application? The third is, how many cameras should you be using for your system? And then I wanted to cover a couple of items more related to objectives and how those influence the rest of your system. The first is the focal length and how that impacts the rest of your system. And then secondly, a compensated versus an uncompensated objective design and the impacts that those decisions have. I did want to briefly touch on a couple of other decision points that should be considered. The first is whether or not you want to use an upright or an inverted style for your microscope. And the second is, what type of illumination style do you want to use? Is it going to be a transillumination, an epi-illumination, or even a different type of illumination? So getting right into it, where should you start when designing your microscope architecture? Well, I always like to start with the sample, right? Because that's ultimately what you're trying to capture your data from, and you want to be able to optimize your system to that sample. So a couple questions to ask yourself when thinking about that are, what are the size and minimum separation of the features that I'm trying to distinguish? Alongside that is, what is the spectral range of what I'm trying to image? So when you combine those two features, you get a requirement for the numerical aperture of your objective. And particularly with that spectral range, you get information on what the color correction requirements are for your imaging optics. Moving on, you'll want to think about how many fluorophores you want to image at once. Since in some cases, our customers are looking to image multiple fluorophores at the same time. So not only is that going to, again, set our color correction requirements if you start having a much broader band that you're trying to image, but it could also set the number of required cameras for your application. If you want to image multiple fluorophores at once, you may need multiple cameras. Next, we move on to a throughput requirement, right? So you're trying to image a certain number of features over time in order to get the amount of data that you need in order to make your product viable. So alongside the numerical aperture, which of course sets how close those features can be together, you're also going to have the size of the field of view of your objective, right? And those two things combined will determine how many features you can image in a single snapshot. And then finally, you'll have potentially some specific cover glass requirements, or maybe even some interference features that are present near your sample plane that could set the working distance requirement for your objective. So thinking about cameras now, we're talking about, how do I optimize my camera selection in order to get the most out of my imaging system? So a couple of assumptions that I'm making here when thinking about camera selection. Based on that previous slide, I've already selected the numerical aperture of my objective in order to resolve the smallest feature that I need to at my imaging wavelength. And I've also set my field of view along with that numerical aperture in order to achieve my throughput requirements. So now thinking about the camera, right, I have a couple of different factors. I have the magnification of my system. I have the pixel size of the camera and the number of pixels or, size of the camera itself. So if I have my diffraction limited spot size in object space, I then multiply that by the magnification and I get my diffraction limited spot size on the camera. That's going to work together with the pixel size in order to ensure that you have proper sampling of that diffraction limited spot, right? So you want to have enough pixels over your area disk in order to ensure that you can resolve your objects. So you want to think about how many pixels you might need for your application. Does it require Nyquist sampling? Do you want to oversample? Or in some cases, you may even be okay with undersampling. Moving on, we're thinking about the field of view on the camera. So again, we have our field of view in object space. We then multiply that by the magnification, and we get the size of the field of view on the camera. So in order to think about that, we need to ensure that we have enough pixels, or our camera is essentially large enough in order to cover our entire field of view. Otherwise, we have wasted the performance of our imaging optics by not imaging that entire field of view. Conversely, you may have too large of a camera, right? Is your camera over-designed for the field of view that you're trying to image? A couple other things to think about when selecting a camera are related to camera alignment sensitivity. And so that's related to the magnification in that with low magnification systems, your camera alignment will be much more sensitive because that magnification gets transferred to object space much more quickly. With high magnification, the camera alignment may not be quite as sensitive. And then thinking about the pixel size, right? As I move to smaller and smaller pixels, I'm going to get less light on each pixel. So I need to think about how much light I need to get a high enough signal to noise ratio in each pixel. So I may need to increase my excitation power. I may need to image for longer, things like that. So the second question is, how many cameras should I use in my application? And I think there's four main decision factors there, right? There's what's the throughput of my system, and then cost, manufacturability, and size. The other question that I might address here is, where do I want to split the light if I do choose to have multiple cameras? Do I want to split it before the tube lens? Most of IDEX health and science imaging optics are designed such that there is collimated space in between the objective and the tube lens. That oftentimes makes it a little bit easier to handle filters and other things in that pathway. And Splitting in that collimated space versus splitting after the two blends in converging space has a big impact on your optical design. So just briefly, I'll cover the baseline case, right? This is just a single camera system where you have your objective, your injection dichroic, your emission filter or filter wheel, your two blends, which focuses that light onto the camera, right? So pretty simple here. This obviously has the fewest components required, so it's going to be cheaper. It's going to be the simplest to align because you just need to align your single camera to the object plane. It's also going to have the smallest footprint relative to some of the other examples that I'll show in a moment. But of course, there's a very large con there, right? You have lower throughput because you can only image on one camera at a time. So your cycle time for your product is going to be longer. So how do I reduce that cycle time? I might think about adding a second camera. So in this case, we're splitting before the two blends. And what you can see here is that there's 4 new components that have been added. The first is an emission splitting dichroic, which is in that collimated space. And then you're basically just duplicating your emission filter, two blends, and camera for your second camera. So a big pro here, right? Now, if you're doing 2-color simultaneous imaging, you've doubled your throughput, which is obviously huge. You can image your sample much more quickly and get much more data off of your sample. There's a couple cons to think about, right? Obviously, we've added components, so that's going to add cost to the system. Another important factor to consider is that now that you have multiple cameras, not only do you need to align that camera to your object plane, but you need to align both of your cameras really well relative to one another. So they need to be in focus at the same time. They need to be detilted relative to one another, as well as in position and rotation. So that's an important factor to consider because now you need to align those cameras really well. And then finally, you've increased your footprint, right? You have much larger size due to the added components. You also may need a larger objective to two blend separation in order to fit that second dichroic in that space. So looking at another 2-camera architecture, in this case, we're splitting after the two blends. So again, we have 3 new components this time. We're not duplicating the two blends because we're splitting after that two blends. So that emission splitting dichroic is now after the two blends. We have another emission filter and the camera. So thinking about that one, again, we've doubled the throughput if we have 2-color simultaneous imaging, so that's great. As compared to the splitting before the two blends, we actually only need 1 two blends, so we've taken out a little bit of cost in the system, and it's a little bit more compact than that other solution. We still have some of the same cons, right? We have more components required than a single camera. We still need to align our cameras really well to one another, but we've added a couple more complications. Since we're splitting now in converging space, we do need to have enough space between our two blends and our camera, so that two blends needs to have a back focal distance that's long enough in order to fit that dichroic. And perhaps even more importantly, we're now going through a plate at 45 degrees while our light is converging, right? So we've introduced aberration into the path that's transmitted through that emission splitting dichroic, and that needs to be corrected, right? So it's going to increase the optical design complexity, and it could also make your alignment more difficult in manufacturing. So now thinking a little bit about the objective and how that impacts the rest of your system. Again, I'm making a couple of assumptions based on some of the previous content, right? First, I know my numerical aperture and my field of view based on my smallest object that I need to resolve, as well as my throughput requirement. And I've set my magnification now in order to match that magnification to the camera. So now at this point, I'm just modifying the focal length of my objective, and I want to see what happens. So some of the benefits of a shorter objective focal length are that you can have a more compact objective, right? So that's going to reduce the size as well as the weight of that objective, which could be beneficial for your focusing stage, particularly if you're kind of on the edge of a weight requirement for that focusing stage. Another important factor is that with the shorter focal length, I have a much smaller filter footprint, especially for filters that are close to the objective. I could potentially reduce the overall track length of my system, right? Because my magnification is set as I move to a shorter objective focal length. My two blends focal length will also be reduced and reduce the track length of my system. On the other hand, if I increase that focal length of my objective, there's a couple of benefits there. The first is now looking in angle space for filters, which I'll show on the next slide. is I have a smaller range of angles in collimated space. So that can help support tighter transitions between excitation and emission bands and make it so that you can collect a little bit more fluorescence. The next benefit there is that our tube lens may be able to be simplified, and this is especially important for low mag systems where you could be getting pretty short focal lengths for your tube lens. So thinking about that, maybe able to simplify your tube lens. And then the last one is kind of a case-by-case basis, depending on how large that space between your objective and tube lens is. But if you have filters that are really far away from the objective, that footprint on the filter could start to be dominated by the higher angle for the shorter objective. And so that's something to think about as well. So I did want to go into a little bit more detail about the impact on the filters here. So the first is looking at that filter footprint, right? So the example I have here is a 0.5 NA objective with a 1.5 millimeter field of view, half field of view. And I have two filters in that space, my excitation dichroic and my emission splitting dichroic. So I'm looking at two objectives, one with a 30 millimeter focal length and one with a 15 millimeter focal length. You can immediately see that the top example with the longer focal length has a much larger footprint on those filters. So looking at on the right with the filter footprints, you can see that the diameter on the top example is almost 53 millimeters on that filter. And if I look at the 15 millimeter focal length objective, that diameter is now only about 32 millimeters on that first filter. So really reduced filter size for the shorter focal length system. That can be particularly helpful for two reasons. The first is obviously your filter is much smaller, so that's helpful in terms of cost. You can get more filters out of a single coating run. And secondarily, it's pretty helpful for wavefront requirements on filters, right? If you have a tight wavefront requirement so as not to degrade your imaging, having a smaller filter to fulfill that wavefront requirement is a little bit easier than a larger filter. Conversely, in spectral space, you can see the bottom example of the shorter focal length has a much larger angular spread on those filters. So what does that do? If you look at the transmission plots of an example dichroic splitter here, you can see that the angular change is causing that spectrum to shift to the left and the right. So we're shifting, a significant number of nanometers as we move to the higher angles. So that can make it more difficult to capture fluorescence, right? Because you either need to increase that difference between the excitation band and your emission band, and therefore make your emission band smaller, or you may need to accept that some light will not be going where it's supposed to, which is probably not what you want to do, right? You don't want to be having light that's supposed to be being reflected, being transmitted, and that's going to be causing a lot of bleed through in your system. Or conversely, light that you want to be transmitted, not actually being transmitted, because then you're going to see darkening at the edges of your image. So something to think about with the objective focal length. We're kind of trading off between that filter footprint and the spectral content. So lastly, I did want to touch on the objective design, right? So we're thinking about compensated or uncompensated objective designs. So just defining that real quick, right? A compensated objective design is an objective that's not well corrected on its own. It requires its tube lens in order to be well corrected for its entire field of view. So if you put that objective on an interferometer and look at it, you're going to get good performance on axis, but you're not going to see good performance for the entire field of view of that objective unless you pair it with its tube lens. An uncompensated objective design, on the other hand, has very good performance for its entire field of view without a tube lens at all, right? So if you move to its entire field of view, you're going to be seeing good performance with that objective standalone. Now, of course, you still need a tube lens in order to form an image, as well as achieve the magnification that you're looking for. And that tube lens needs to not degrade that great optical performance of your uncompensated objective. So a couple benefits of a compensated design are mostly related to cost and size, right? So if you have that compensated design form, what you're doing is aberration balancing between the objective and the tube lens. And typically that allows you to use fewer elements in order to achieve equivalent optical performance. So that could reduce your size, weight, or cost of your objective. On the other hand, with the uncompensated design, you're now looking at quite a bit relaxed alignment tolerances relative to the compensated design. So your objective and your tube lens don't need to be aligned quite as well to one another as you do with the compensated design form. In addition, it's a lot easier to test because now you can test your objective standalone without a tube lens and look at its entire field of view and ensure that your objective is really great before you pair it with any sort of tube lens. And then finally, and I think Joe is going to go into a lot more detail on this, but the uncompensated design forms can easily pair with different focal length tube lenses in order to change your magnification. So Joe's going to talk about our new XPLAN line of lenses, which are uncompensated design forms. So I thought this was a good transition. Take it away, Joe.
Well, thank you, Jim. So first off, I'm really excited to be able to show you all this new line of objectives and tube lenses that are carrying the Melles Griot brand. We call it the XPLAN CCG lens series. So that term XPLAN is really referencing an old industry standard term, plan objectives. These were objectives that historically delivered a more flat field image compared to other objectives. So in other words, the image quality didn't change much over that field of view for that objective. So we're calling these optics XPLAN to refer to an extended flat field of view that they are all designed to image over. And CCG is referring to, or rather stands for, configurable cover glass, which I'll speak to shortly. So first, let's just discuss at a high level some of the main trade-offs that we see between instruments that utilize commercial off-the-shelf assemblies and components versus instruments that utilize custom solutions. The commercial off-the-shelf instruments generally suffer from imaging performance variability, particularly over the field of view. Generally, they only support a smaller field of view, and if they can image over a large field of view, the quality degrades significantly, especially as you go out towards the edge of the sensor. The commercial off-the-shelf solutions, they're limited also in their flexibility for your specific application. So what that means is that generally you're forced to find something maybe close, but not exactly optimal for what you're trying to do. Or you even have to adapt your own specimen to adjust for what happens to be available off the shelf when it comes to working distance or cover glass considerations, for instance. But the great thing about the off-the-shelf solutions is that you can get them in a relatively short time frame and start imaging, using them right away. On the other hand, when you think about custom solutions, they're great because you can dial in really high performance over a large field of view. You can do it specifically for your application, for any constraints you have. So the flexibility is really, really high for custom solutions. But the hurdle is that you have to wait a long time to get your first article. And generally, you have to pay NRE associated with all the design work. So we see the XPLAN CCG lens series as being a powerful new third option that really combines the benefits of the off-the-shelf solutions and custom solutions, while at the same time minimizing or even eliminating the disadvantages of either. These lenses offer a very high performance while maintaining very high flexibility so that they can work with many different fluorescence applications, and you can still benefit from the relatively short lead time compared to a full custom solution. So, which objective should you choose in the XPLAN line? Well, IDEX understands that there are a lot of factors that go into ultimately choosing what objective you're going to go with on your instrument. You could be maybe focusing on the most obvious thing. What am I trying to resolve? Or maybe said another way, how close can my objects be to each other so that I can resolve the two different objects, right? Questions like that point you right to an NA and it will help you select your objective. But there's other things too. The spectral requirements for your imaging, working distance requirements, maybe for sample clearance limitations or constraints, size or weight limitations having to do more with the system. So the idea, though, is that the XPLAN line, these three objectives, they're really were designed with the goal of getting the majority of important imaging parameters for fluorescence microscopy very close to optimal, thereby making your alpha instruments far more useful and helping you understand far more precisely what specifications you actually need for your application going forward. When it comes to selecting a tube lens, well, this usually falls a lot lower on the list of priorities when it comes to speccing out a microscope. But IDEX, again, understands that getting the right tube lens is critical in order to get the flat field imaging out to the corners of your sensor while simultaneously providing very low optical distortion. So answering questions like these will lead you to one or another of our XPLAN tube lenses. What pixel sampling am I trying to achieve for my resolution limit, my minimum feature size? Or what field of view am I targeting for my throughput? Or it could just be something simple like, hey, I already have a sensor. What's the tube lens that's going to fill it correctly? So this is what the full series looks like to date. Any of the XPLAN objectives are going to work flawlessly with any of the XPLAN tube lenses, while at the same time providing flexibility in the size of the collimated gap in between them. So that collimated gap is really what's needed to accommodate one or maybe two different dichroic filters and an emission filter. And on the far right, you can see the relative sensor positions based on the tube lenses. So in this slide, we're focusing on matching the optical bandwidth to the bandwidth of the sensor. This is essential when it comes to maximizing instrument throughput. So the bandwidth, when I say that, it's really just another way of saying the full information content. So as you can see, the optical bandwidth of the XPLAN line, it's shown in the red box down in the lower right. It depends significantly on the wavelength that you're imaging with. Generally speaking, just to paint a broad stroke, that XPLAN line is matching to about 20 megapixel sensors. And so the bandwidth of XPLAN also, as you can see, varies somewhat based on the objective that you select. But the information content of the optics does not change based on the tube lens. And all that is to say is that the tube lenses are essentially taking all of the information from the objective and mapping it to different sensor sizes. So it's not limiting in any way. Now, pay attention to the equation in the middle. That has to do with the pixel size that would hit that minimum 2 pixels per airy disk radius condition that's shown on the slide. That's all well and good if you can hit that. But this equation does not account for the real effects of optical aberrations that come from the optics. This is a key point. So off-the-shelf lenses might be giving you good pixel sampling on axis in the center of your field of view, but because of field aberrations coming from the optics, the amount of useful information gets throttled down in reality to some much lower value, overall decreasing the information content of your instrument. So to discuss the difference between off-the-shelf and the XPLAN line a little bit further, notice these two graphs. They're both showing RMS wavefront error versus an angular field of view through just an objective lens. On the left side, you see the orange line that's showing a typical off-the-shelf objective performance. So you can see on axis, in the middle of your field of view, your aberrations are generally low and well controlled, but somewhere within the field of view of that objective, that wavefront error increases above the diffraction limit, thereby limiting the amount of usable data that you're getting with each image. Now notice the green line on the left. This is showing a typical XPLAN nominal design performance. And notice that that line is staying well below the diffraction limit everywhere in the field of view. This is on purpose because it allows for what's shown in the blue line, which is a typical as-built lens performance that stays below the diffraction limit over the entire field of view. The graph on the right is just showing real wavefront measurements that we've taken of our XPLAN objectives over their full angular field of view. So all that is to show that the imaging performance goals of the XPLAN optics are realized in the actual unit builds. So again, with the tube lenses now, maybe you've heard this belief, or maybe you've even had it. Just give me a magnification, give me the right focal length for the tube lens, maybe just a couple doublets. I don't have to worry about it very much. It'll be fine. IDEX understands the benefits of having an optimal tube lens and the consequences of having a suboptimal tube lens and how that can really make or break the imaging performance over your entire sensor. So this graph is again showing RMS wavefront error versus the same angular field of view, but now we're just considering the effect of the tube lens imaging with a remote pupil, just like in a microscope. So the yellow line is showing what you can expect over the full field of view when you use some off-the-shelf doublets. So similar to the off-the-shelf objective, on axis in the center of your image, well, it's usually going to look fine. But somewhere in the middle of the sensor again, the image quality is going to degrade significantly enough to limit the amount of information that you're able to get from that image. So the red, gray, and purple lines shown at the bottom, those are again as measured real wavefront measurements that we took of our XPLAN tube lenses over their full angular field of view. You'll notice that the goal, the design and build of these tube lenses is to maintain that flat field imaging that's already coming from the objective lens. So it's important to note here that combining an XPLAN objective with an off-the-shelf tube lens with bad performance, it would be a terrible waste because you'd be losing all of that good imaging coming from the objective. Look at what the tube lens alone could be doing to your imaging performance. So really, you want to utilize both the XPLAN objective and tube lens together. This slide shows how basically each XPLAN assembly, whether it's a tube lens or objective, gets tested. We verify the wavefront performance at many field locations everywhere in its field of view to ensure that you're going to get a fully flat and usable field of view when you put a sensor in place. So although we guarantee performance over the full field of the optics, we regularly test beyond that to what we call an extended field position. And the purpose of this is twofold. It allows for slightly larger sensor sizes or different sensor sizes to still be filled with good performance, as well as allowing for misalignment of the sensor and illumination during integration without having to suffer a sharp drop-off in performance. And if our standard metrology package needs to be enhanced for your application, we're very much open to discussing that with you. This is my last slide. To conclude, I want to revisit the idea of the flexibility of the XPLAN lens series. So before the build and test of your objectives, IDEX engineers are going to collect as many specifics as they can, as are available, about your instrument or about your application. The big ones that we're looking for are, what is the spectra that you're planning on using? What are the spectra that you're planning? What are the details about the cover glass, the material, the thickness? And this third one is significant. Are there specimen details? Now, that isn't always the case, but in other words, you might actually be imaging through a known thickness of buffer solution. And so if that's the case, your XPLAN optics will be delivered factory adjusted to whatever those specifics are, thereby giving you an optimal performance for your application when you integrate those optics. So all the objectives are also fully compatible with the Dover DOF5 focus stage, but there is far more to discuss as it pertains to the motion control solutions for a microscope. And for that, I will turn it over to Kevin McCarthy of Dover Motion.
Thanks, Joe. And congratulations on the XPLAN launch that really bridges an important gap between underperforming off the shelf and high performance, but really expensive, really long lead. So we're going to shift gears and go from optics to mechanics, and in particular, precision motion. So the fundamental question about what's the motion doing in the system is driven by the fact that while the field of view is typically really small, it can be a fraction of a millimeter to some single-digit millimeters, the sample is typically much larger. Examples could include a microtiter plate, or a flow cell, or an array of slides. But the bottom line is that since the sample is considerably bigger than the field of view, we're going to need to move to get to the entire sample. Similarly, there's a trade-off in the vertical direction, the focus axis, and there the depth of field is frequently a lot smaller than the planarity of the sample or the curvature of the device that the sample is on, flow cell, microtiter plate, etc. So generally speaking, to be in critical focus, and especially if you're doing volumetric imaging, you need to focus the objective, move it in Z, and do so at a very high resolution, especially as the numerical aperture goes up. There's another set of motions that may or may not be necessary. If the local sample curvature exceeds the depth of field, that is to say, in a single field, then you may need to tip and tilt the sample so as to keep the local field of view normal to the optical axis, and that may change over the travel. There's basically two fundamental techniques for imaging, and they directly impact the choice of the motion system. These are what we refer to as sequential field imaging, in which you move, stop, take a picture, and do that over and over. And in that case, the attributes that we want out of the motion system are to move really fast and hold really still. There's an alternative imaging technique, which is called TDI-CCD scanning. And in that case, there is no discrete field-to-field motion. The stage and the sample scan continuously at constant velocity, and images are acquired continuously. We'll see both of those modalities coming up. So when we look at sequential field imaging, in the illustration below, the blue curve would be velocity versus time as we move from one field to the next. When we settle into the new sample position, the stage is fully stopped, we turn on the illumination, which is the red bar, and we begin integrating the photoelectrons. When sufficient signal is acquired, we turn off the light and we race like crazy to get to the next field of view. Now, there's something else that happens during that move, which is typically that the image is downloaded from the camera. And then this is repeated over and over again. Here's an example, and in fact, it's actually this flow cell I'm holding up, where the flow cell has 17,440 fields of view, and these may have to be visited in multiple colors and may also be visited many times over the course of an instrument run. And in this case, the fields of view are the little squares on the left. There's 218 in a row, and basically it's moving, move, stop, take a picture, move, stop, take a picture down the row, step over, reverse direction, and then continue, complete that lane, and then 8 more lanes for the total number of fields of view there. That's referred to as serpentine stepping. The alternative is TDI CCD scanning. And in that case, a single physical point on the sample is imaged as a virtual pixel up on the sensor. And as the sample moves at constant velocity, that virtual pixel moves from row to row on the sensor and accumulates photoelectrons all the way until it gets to the end, at which point it's read out. So the sample illumination, motion, and image download are continuous and occur simultaneously. Now we look at motion system architectures. There's a variety of ways to skin the cat. We can put the sample on an XYZ stage, move it in 3 axes, and keep the objective and all of the optics, including the camera, fixed. An alternative is, this is a pretty common one, we move the sample in X and Y, and we move the objective in Z. There are others. You can split it up. You can also have the sample stationary and move the entire optics and objective in X, Y, and Z. There's 2 fundamental bearing technologies, crossed roller, which provides the smoothest performance, and recirculating bearings, where the balls literally recirculate. This is useful when you need an extended travel on one axis, which is frequently the case if the sample is being presented to an operator for loading and unloading. And then we come to the architectures of the motion controller. Traditionally, multi-axis motion control has required a box, sometimes a large box, even a rack mount box of electronics that somehow has to get shoehorned into your instrument. At Dover Motion, we've really pioneered a fundamental change in this paradigm, in which we have developed our smart motion control approach, in which the motion control electronics is miniaturized and put into each of the individual axes, with the only need for cables being DC bus and communications. Here's a few of the examples in our smart stage ecosystem. We have single axis product. Stacking them generates an XY stage. For transmissive illumination, we have our open frame, smart open frame. Over on the right, we have our award-winning DOF5, which is a dedicated focus stage. And a more recent introduction has been the Z wedge that you see in the next to the DOF5, which is typically used to move the sample in Z as opposed to the objective. We also have very advanced algorithms to really deliver our goal, which is the highest possible imaging throughput. Some of those advanced algorithms are listed here. They include the ability to provide very precise triggers at explicit positions. And this is typically used for TDI CCD imaging, but it could also trigger a camera. And we'll get to this a little later, but we have a very powerful technique called repetitive motion enhancement. And this is fundamental to being able to drive throughput as high as possible. We have very high resolution encoders. Our latest Dover Motion Ultra encoder, the resolution is 305 picometers, which is essentially 1 aluminum atom. We have position accuracy compensation, which means that we don't have to make a perfectly accurate stage. We can study how the stage performs with a laser interferometer, record that information, and basically play it back in real time forever after, making a very precise stage without driving a lot of cost into it. We also have our Motion Synergy API, which dramatically simplifies the program. We had loved this. One of our customers, when we asked how they had found working with that, he said, "Oh, I had it up and running by lunch." That's pretty nice to hear. So we mentioned focus stages, and here are two, one for samples, one for objectives. Traditionally, focus motion is done with lever amplified piezo flexures, but it turns out while they're dominant from a market share perspective, they're really a pretty terrible technology. And we think we've really come up with a far better one with 5 millimeters of travel, 5 nanometers of resolution, and all of the drive control built right into the stage. Generally speaking, though, a Z stage is very good at moving the objective or moving the sample, but it doesn't really know where to put it, and that's where you need an autofocus. And generally speaking, that's either done with an inexpensive but sluggish contrast-based system or a fast epi, which is to say through the objective, laser system. Now, in the real world, you have people walking by, people bumping things. There could be somebody on the next bench vortexing or centrifuging. There's environmental vibrations in where the systems are set up, and you're not going to get super high resolution imaging without doing something to mitigate that. And that mitigation is typically to employ some sort of vibration isolation system. And they're effective at eliminating certainly high frequency accelerations, but they actually provide resonant gain at low frequencies. And in particular, they react to the inertial forces of our stage, which if we're making very many frames a second, are actually serving as a forcing function that is potentially driving significant vibration into the system by virtue of the natural frequency of the isolation system. We have advanced algorithms that fully suppress the reaction of the isolation system and the inertial forces of the stage. And as a result, we drop in at the end of the move, and we do not wait a long time to settle. We just drop right in. Here's a typical example, a 1 millimeter move, settling to plus or minus 50 nanometers, and doing so in under 30 milliseconds. In addition to the stages and the optics, something has to knit all this together, and that's generally speaking the structure of the stage. And we're very good at working with metal and often help our customers and our partners to develop the structures needed to hang all of the right things at the right places. And then we also have significant experience in integrating optics, motion, vibration isolation, and structure. In that middle picture, we have 4 20x 0.8 numerical aperture objectives on a 36 millimeter pitch, each with its own Z stage, each with its own laser autofocus, and ultimately each with its own camera. We're also really good at working in very compact spaces. So when the overall goal is for the instrument to be compact, we can really excel. And there on both sides of that are 3-axis complete microscopes with illumination, multi-channel fluorescence, 3 axes of motion, and yet you can hold them in the palm of your hand. So with that, we'll turn it over to any questions that folks might have. Surely there's got to be a few.
There are. Thanks, Kevin. And thank you to all the presenters. That was really great. Really great educational information. We did have a couple of questions come in, so I'll address those now. And feel free, folks, if there are any additional questions, to go ahead and pop them in the Q&A. We'll try to get to as many as we can in these last remaining minutes of our session today. So let's see. The first question that came in was, how do you maximize imaging throughput?
Yeah. Well, either party could probably take that one. Maybe I'll start. It's a broad question. And certainly there are optical aspects, there's illumination aspects, but there's definitely motion aspects. And part of it depends upon whether you're going to be doing a constant velocity scanning system or a sequential field move from field to field system. In the latter, the first impulse is, oh, I know, I'll hit it harder. If you give it more current, give it more force, higher acceleration, half G, 1G, 2G, the move will take place in that much shorter a time. It's not linear, but the problem is when you hit it harder, the inertial forces go up and the whole thing can start to bounce, and you may end up, it may be self-defeating, and you have to wait until the vibration isolation system stops bouncing around before you can begin acquiring your image. And that's where our advanced algorithms totally squash that. We'd have to really go into the details of each application, but we have the tools. In many cases, our following error is 0 before the end of the move. So at the instant the move is complete, we're ready to begin imaging. Now, one of the qualifiers is, though, as we shrink the time that it takes us to get from field to field, you have to make sure that your camera doesn't become the long pole in the tent. So you may find yourself going from USB 3 to gig-E to 5 gig-E to 10 to 25 gig-E to get all of those pixels downloaded quickly enough to before we're ready to make the next move.
And I'll take the optical part of that that question. It's a good question, and there's really a lot to it. But to boil it down in an optical sense, it has to do with matching, again, the bandwidth or the information content of your optics to the information content of your sensor, which is in units of megapixels. So really being able to get the right match there is important. But then the second part of that is, how good are your optics? Are they actually going to be able to maintain that sampling, that matched sampling that you're counting on all the way to the corner pixels in the sensor or not? And so that's where high quality optics that are well matched for your sensor really come into that.
Great. We had another question just pop in. How does the objective mass affect movement and settling times in the DOF5? Oh, Kevin, you're on mute.
That depends a lot upon the type of objective. If it's a small commercial off-the-shelf objective, these are typically a couple 100 grams, and that is essentially 0 consequence. Where things get trickier is as you start to get into bigger objectives, such as the one we're looking at here. And in particular, it's not just about the mass, it's also about the moment. So for example, if parts of your optical structure require that the objective be substantially spaced out from the DOF5, then the polar moment of inertia is going to set a fundamental resonance, which is going to limit your bandwidth and your performance and your settling. So we always try to keep the mass of the objective as efficient as it can be, but more particularly mount it as close to the DOF5 as possible. And then for those applications where the objective does have to stick out a ways, we have other products such as our Smart Stage 50, which has larger bearings, longer bearings, and is better suited to handle the excess moments that some applications require.
Awesome. Well, thank you so much to all of our panelists. This was really, really great. And to all of our attendees. Again, we'll send you the link to the recording after the webinar, and have a great afternoon. Thanks.